Event-based simultaneous localization and mapping by William Chamorro, Juan Andrade Seto, and Joan Solá. Event-based cameras are video-inspired sensors that respond to changes in brightness generating events. As soon as these changes exceed a threshold, a positive or negative event is fired. Conventional cameras provide frames, while event cameras give asynchronous events at a microsecond resolution. Event cameras exhibit a high dynamic range that makes them suitable for challenging lighting conditions like overexposure or poor illumination. We deal with the SLAM problem by solving the tracking and mapping in parallel threads. The tracking thread estimates the camera pose using line and events, while the mapping thread builds a semi-dense reconstruction from which we recover and optimize 3D lines. Both nodes are constantly sharing information and running on real time. We use the Davis model that provides grayscale images and events. The image is used to estimate the initial camera pose. After that is no longer required. To evaluate the tracker, we set a group of lines whose 3D coordinates are well known. Once we have a pose estimation, the lines are reprojected using this pose. The camera pose is estimated using an extended Kalman filter that minimizes the reprojection error between lines and events. To this end, we have implemented several filter variants to determine the best tracker response. Using the constant velocity model, we test our tracker with high dynamic motions by shaking the camera as fast as possible by hand. Also, we introduce illumination changes by turning on and off the lights of the lab. Note that despite of these changes, the tracker is still estimating the camera pose with a low error. In another experiment, the camera is static and a motion-constrained device gradually increases speed until the tracker starts to degrade. The mapping thread is based on the event-based multi-view stereo by Henry Rebeck, from which we create a 3D reconstruction using lines. We use a projected grid assorted in inverse depth, and its voxels are filled with votes from the events in different positions along the camera trajectory. After a maximization process and filtering stages, we create a disparity space image from which we are able to recover 3D lines. This parallel tracking and mapping approach is intended for man-made environments where the stride segments can be recovered from the edges of things. As the camera moves, new lines are discovered and added to the map. The bundle adjustment algorithm collects the lines and their events from a few past frames and correct them using nonlinear optimization. Note that the tracking and mapping threads are running in real time. The three-edral scenario used to evaluate the tracker was also mapped using just a few lines from the beginning as a bootstrap. Here, a lot of lines can be recovered and observed several times, so it allows us to visualize how works the bundle adjustment. In another test, we map an office which has objects far away from the camera. It's important to mention that the success of the algorithm lies in the contrast of the scene and in the straight edges that can be recovered from the things around the environment.